Lesson 29, on to Unit 5, I believe the last chapter of material in pre-calculus. So, in my opinion, the only difficult part about this entire chapter is being able to recognize the patterns. Okay? If you have difficulty recognizing the patterns, that's where you're going to have difficulty being able to do a lot of the problems in this section. Otherwise, it comes back down to just a set of formulas and identities that we have to follow. Okay? So what you're going to want to do in this unit is make sure you know the formulas and practice the techniques to recognize the patterns. Okay? Now, let's start with some definitions here and talk about what they mean. Sequences. That's an extremely important definition to understand. Now, an infinite sequence is a function whose domain is the positive integers and whose range is a set of real numbers. That almost means nothing to some of us, okay? Think of it this way. The values that I plug in are only positive whole numbers. So I can only plug in 1, 2, 3, 4, 5, and so on and so forth. The numbers that I can get back are any possible real numbers. So it can be anything from radical 2, radical 3, radical 4, radical 5. It could be pi e. It could be an assortment of fractions. As long as it's a real number, we can get that number back. Now, what's important about the sequence is that it's a list of numbers. Okay? It's one after another. Now, every element in the range of a sequence is called the terms. So, this notation that's written here, I don't like it. Okay? We're going to go through it, but I'm going to go ahead and do it in a different way. Now, example 3a, it says, given this sequence, f of n is equal to 2n minus 1. Now, we change patterns to, instead of using x in here, we use n, and the reason for that is because we're talking about whole numbers, not any number. X generally refers to any number on the coordinate plane. We're talking about only the whole numbers, okay? 1, 2, 3, so on and so forth. So, what is the first four terms of this sequence? So, well, on my scrap paper here, you'll notice I wrote down the sequence. Now, a sub n, this is the notation for a sequence, okay? So instead of writing f of n, we write a sub n to denote a sequence. This is going to be a list of numbers. Now, I want to know what the first term is. Well, that's replacing n with 1. The first term will always replace n with 1. Okay, so what is the first term? Well, it's 2 times. If I replace my n with 1, I get 2 times 1 minus 1. 2 times 1 is 2, minus 1 is 1. Okay, what's my second term? A sub 2 is going to be my second term. It's when I plug 2 in for n. That's 2 times 2, which is minus 1 is going to be a 3. So my first term is 1. My second term is 3. Okay, let me go to the next one. A sub 3 is going to be 2 times 3 minus 1. Again, replacing my n with a 3 now. That's going to be 5. And the next one's going to be 7. I can actually anticipate the next set of numbers. Okay? It's going to be 9, 11, 13, 15, 17, 19, 21, 23. Do you notice a pattern about all those numbers? This right here is the mathematical definition of how we would define an odd number. Okay, 1, 3, 5, 7, 9, 11. Again, if you do the next one, a sub this is 4, a sub 4 is this. Okay, a sub 5 would be 9. If you don't trust me, plug it in. If I plug in 5 to here, I get 2 times 5 is 10, 10 minus 1 is 9. Okay, now how would I write out these terms? I want to use this little set bracket notation. Okay, this stands for set bracket. Now, keep in mind this is not a hard bracket like this. It's not the open parenthesis like this. It is that squiggly bracket. Make sure you try your best to write it like that. Okay, and I write 1 and then 3 and then 5 and then 7, and I'm going to put dot 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 because this does continue on forever. Okay, it doesn't tell me where to stop. It doesn't tell me where to end. So I'm going to stop at dot dot dot. It continues on forever. Now, I want you to also know that when I write the set notation out like this, this is a sub 1, a sub 2, a sub 3, a sub 4. When a set is written like this, that's what you can expect to know, is that the first term is a sub 1, the second term is a sub 2, and so on and so forth. So that is part A. A, okay, is that right there. Those are the first 4 terms. 3B asks us, what is the nth term of the sequence? Well, this one's kind of obvious. This is the nth term, okay? A sub n is equal to 2n minus 1. If I plug in any number n for the nth term, I'm going to get that particular number, okay? Again, keep this in mind. This is the nth term. 3C asks, what is the 12th term in the sequence? Now, what am I looking for? I'm looking for a sub, well, 12. So in here I'm going to go 2 times 12 minus 1, that's 24 minus 1, that's 23. It is very easy for me to identify the 12th term when it's in this form, okay, when it's written in this form. Now, you'll notice next up in my notes, the nth term of a sequence can be written as a sub n, and that's what we're going to do. That's the notation we are going to use. When I ask you what is the nth term, you write a sub n is equal to, and the equation for the generic term, okay? Now, example number 5 says find the terms of a sequence. Now, find the first 3 terms of this particular sequence. So let me go ahead and write that down. I have 5a, and the sequence is 1 over n plus 1. Now, this is, again, the nth term of the sequence. So if I want to know the first 3 terms, I want to know a sub 1, I want to know a sub 2, and I want to know a sub 3. Well, what happens when I plug in 1 for n? Again, that's all I'm doing. I'm replacing the n that's here with this number here, 1. So I have 1 divided by 1 times 1 plus 1. That's going to be 1 over 2. This is 2, and then 2 times 1 is 2. So 1/2 is the first term of the sequence. What's the second term? Well, I have 1 over, replacing all of my n's in this formula with 2 now. So 2, 2 plus 1. So that's going to be 1 over 2 times 3, and 2 times 3 is 6. So 1 over 6 is my second term. And the third term is going to be 1 over 3 times, and I hope you see the pattern here. This is 1 times 2, 2 times 3, 3 times this should be 4. Okay? And this will be 1 over 12. And you'll notice, again, this is 1 over the nth term, the nth piece, times the next number. So 1 times 2, and then 2 times 3, and then 3 times 4, and the next will be 4 times 5, and 5 times 6, and 6 times 7, and so on and so forth. So the way I'm going to write this out is this is the set, and again, this is a terrible bracket that I just drew here. It doesn't matter as long as you try and give me the fact that there should be that little bump in there, okay? 1/2, 1/6, 1/12. And you can give me the dot, 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 because this continues on forever. Those are the first 3 terms of my sequence. Let me flip over. We're going to just go ahead and keep on going in this same video. We're going to do 5b here as well. Now, 5b asks, what's the 8th term of a sub n is equal to 2 to the n divided by n to the power of 2? What is the 8th term of this sequence? Well, how do I find the 8th term? Well, just like we did in the last one, I plug in the numbers that I need. I plug in 8 for this particular n. So what is this going to be? Well, on the bottom, that's 8 to the power of 2. That's 64. And then on top, I have 2 to the power of 8. 2 to the power of 8, that's, well, 2, 4, 8, 16, 32, 64. And that's 64 at 2 to the 6th. So I have 2 to the 2 more, don't I? Again, I'm going to do that one more time. 2, 4, 6. I'm going to do it here. 2, 4, 6, 8, 10. Sorry, 2, 4, 8, 12, or 16, 32, 64. I get back to 6 of them. I have 2 left. These will cancel out, and I'll be left with just a 4. That is the 8th term of this sequence. Okay, the 8th term of this sequence is 4, and that's all I need. Okay, let's actually continue moving. Alternating sequence. Okay, this is logically explained. Okay, an alternating sequence is one in which the signs of the terms alternate between positive, and negative. So what is one example of an alternating series? Now, there's an example of this in your textbook. I'm going to give you one here. An alternating sequence will always be something that looks like, say, this. Okay, that would be an alternating sequence. Because if I start plugging in numbers, let me go ahead and do a sub 1. A sub 1 is going to be, well, I don't want to make this as difficult as possible. Let me just cut out this bottom piece. It's not necessary. So let me plug in 1. I get a negative 1 to the power of 1 times a 2. So negative 1 times 2, that's going to be a negative 2. What if I plug in 2? Well, if I plug in 2 now, this is 2 to the 2, that's 4. But negative 1 to the power of 2 is a positive 1. That gives me a positive 4. If I do a sub 3, and I hope you recognize the pattern, negative 1 to the power of 3 is going to be negative 1. 2 to the power of 3 is going to be 8. This becomes a negative 8. And then a sub 4 is going to be a positive 16. A sub 5 is a negative 32. A sub 6 is going to be a positive 64, because I'm just multiplying each thing by 2. Again, that's what this is saying. It's 2 to the power of n. For every next term, I have a multiplication of 2 more. And a multiplication of a negative 1. Multiply this by a negative 1, or technically a negative 2, I get a positive 4. Multiply by negative 2, I get a negative 8. Multiply by negative 2, I get positive 16, and so on and so forth. We're going to go ahead and do recursively defined sequences in the next video, because those ones can be a little bit annoying.